I sure like cupcakes. A minus 20 degree cupcake is pretty cold, but then it was left out at a room temperature of regular 20 degrees. Now it took 30 minutes for that cupcake to become 0 degrees, and we know that apparently the best time to eat that cupcake is minus 10 degrees. Hindsight's 20/20, and we can use Newton's law of cooling to determine when that cupcake should have been eaten. First, let's pick out the information from the paragraph and translate it into functional notation. Minus 20 degrees, that was the initial temperature, T of 0. The room is regular 20 degrees. We call that T sub S, the temperature of the surrounding. We know the temperature became 0 degrees after 30 minutes, or in other words, T of 30 equals 0. The question is when? At what time does the cupcake become minus 10? In functional notation, we'll say T of what equals minus 10. We can plug all of this into Newton's law of cooling. If you recall, the temperature of an object at time t, the solution of that differential equation was T naught minus T sub S times e to the minus kt plus T sub S. Time to plug in what we know. We have T naught, T initial, this was minus 20, minus the surrounding temperature, minus 20, e to the minus kt, plus the surrounding temperature, plus that 20. We can reduce this just a little bit. Minus 20 minus another 20, that's minus 40. E to the minus kt plus 20. And if we knew k, that would be great because then we'd be able to tell the temperature for any time we want. Let's use that last piece of information. T of 30 equals 0. This means we get an output of 0 if we plug in 30 for t. So this would be e to the minus k times 30. Plus 20, this lets us solve for k. Let's do just that. Subtract 20 from both sides. Minus 20 is minus 40, e to the minus 30k. We can divide both sides by minus 40. 20 divided by 40, this will be a half. Those negatives will cancel out. E to the minus 30k. To undo the e, we take the natural logarithm of both sides. That should undo everything. This would mean that natural log equals natural log of e. ln and e undo each other. Those are inverse functions. Natural log of a half, this will be minus 30k. Last thing to do to solve for k, divide both sides. K will be natural log of 1/2 all over minus 30. In usual fashion for these questions, we can go ahead, take this value, and plug it in to our big equation. We get that our full temperature at time t is minus 40 e to the minus natural log of 1/2 over minus 30 t plus 20. Certainly we could cancel that negative over a negative if you like. So this gives us the temperature of our function at any time we want. What was that question? The question was T of what equals negative 10. We're ready to answer this. We can set our equation equal to negative 10, solve for T. It'll be a very similar process. Minus 40 e natural log of 1/2 over 30 plus 20. A similar process, subtract 20. 10 minus 20 is minus 30, is minus 40 e natural log of 1/2 over 30 times t. Divide both sides by a negative 40. Negative 30 over negative 40, this should be 3/4, equals this e. And once again, to undo the e, we'll take the natural logarithm. Natural log of the left equals natural log of the right. We do it so the e and the ln cancel out. How nice. Natural log of 3/4 equals natural log of 1/2 over 30 times t. Almost there. If we want t all by itself, we can just divide by whatever's next to it. Divide by natural log of 1/2, multiply by 30. I think we're getting this t value. 30 natural log of 3/4 over natural log of 1/2. If you were to put this in a calculator in minutes, this would be about 12.5. Not too long to wait. You can't get very distracted if you want to eat that at an optimal temperature. There was a lot going on here. We really had to pick out the information from the paragraph and interpret it correctly. Plenty of back and forth, plugging things in, solving, and then replugging things in. Very classic with these types of exponential equations. I think this is a great question and it might be worth your review.